This video is for Math 1332, and it's meant for Monday, July 17th, which is the day we're scheduled to work on sections 1.1 and 1.2. Go into My Math Lab, sign into your account, and then open up the 1332 Summer 2023 class. Over on the side, there's tabs. You're looking for one that says Assignments. And we're going to do these first two, 1.1 and 1.2 today. 1.1 is inductive and deductive reasoning. So each thing you see here is an assignment you need to work on. The due dates are right next to each assignment. And we do 8 sections per week. So this week we're going to be doing 1.1 and 1.2 on Monday, then 1.3 and 2.1 tomorrow, 2.2 and 2.3 on Wednesday, 2.4 and 2.5 on Thursday. And then you get a 2-day window, Friday and Friday and Saturday. 2-day window, Friday and Saturday. And that's why all these assignments are due Saturday night at 11:59 p.m. So you just do the homework and use these videos to help you do them all, but then you can do problems more than once to practice for tests, and then there's nothing on the tests that aren't in the homework somewhere. So if somebody said, I understand all the problems on all 8 of these first 8 homeworks, then that would be the key to doing well on the test. The test will appear right here in the assignment list. It'll appear right between 2.5 and 3.1. It just won't appear here until Friday, July 21st. So that's when it's not visible till you can open it up and take the test. And there's only 1 attempt per test, so don't open the test. When it appears on Friday, the 21st, don't open it till you're ready to take it. Because if you open it, it's got an hour-and-a-half time limit, and your time will start as soon as you start working on it. So I just clicked on section 1.1. This has 15 questions in it. Loading this now. Okay, so the first idea here is something called a counterexample. And this is a way to prove a statement false. You can prove a statement false if you can come up with one example that shows it false. You can't prove a statement true by one example that shows it's true, but you can for the false side. So supposedly the statement is right here at the top: no U.S. president has been younger than 65 at the time of his inauguration. Use the table below. So they just picked out a handful of presidents here and told you their age when they were inaugurated. And it says no U.S. president has been younger than 65, but actually 4 of the ones on here were at their time. So, and you only have to come up with one example, but here it does say select all that apply. Normally you just have to come up with one example. You could say Teddy Roosevelt was only 42 when he was president. And normally that would be enough to show that it's not a true statement, but they just want me to check all. John F. Kennedy was 43 when he became president. Barack Obama was 47, and Harry Truman was 60. But there were 3 presidents that were older than that were not younger than 65, so that those 3 would have worked. But see, that's why you can't just look at one and say, oh, Ronald Reagan was 69, that means it's true. No, it takes more than one to show that it's true. So when you answer a problem, you check it. If you get a green check, then that means that problem's correct. Now, even though the problem's correct, I could do it again. So until the deadline on Saturday night, you can go back in and try problems again. And the good news is, if you get them right the first time and get them wrong the second time, you can click an option to save your best score, and then you don't lose any points by doing that. So if you work all the homework, you might get 100 on all the homework grades, but that's not a guarantee that you're ready to take a test yet. Sometimes it takes more practice than just that. I can make this bigger so you can see it more. Oops, it's going the wrong way. Here. There. Okay, so find a counterexample. If a number is multiplied by itself, the result is even. So all I need to do is find one time where two numbers multiplied together are not even. And it actually happened 2 of the 4 times here. Well, 2 of the 4 times I didn't get an even answer. There's 2 even answers here. But if a number is multiplied by itself, so 5 times 5 equals 25, that's a number multiplied to itself. But I didn't get an even. I got an odd answer. So that proves it false because I found one example that proved it false. And the answer is not B. This is not like the previous one where you want to check all that apply. This is a regular multiple choice question. And even though B might appear to be wrong because the answer is odd, it's not meeting the first half of the problem about a number times itself. This is 3 times 5, so that's not a number times itself. And even C is a number plus itself, so that doesn't count. And then D has a number times itself, but D actually shows that the statement's true, but that doesn't prove that it's always true just because one example works. So this one is only A. Same thing here. Find a counterexample. Adding the same number to both the numerator and denominator, top and bottom of a fraction, does not change the fraction's value. Adding the same number to both the top and the bottom. So first you want to see, are they even violating what they said in that statement? Adding the same number. See how the D is out? D is out already because they're multiplying by the same amount. And whether that works or not doesn't matter here because we're trying to show that adding the same number does not change it. So D is definitely not our counterexample to prove that this is false. In A, they added the same number to the top and bottom, and they got 7 over 7. The fraction 7 over 7 is not equal to 3 over 3. Or they added 0 to both of them. 1/2 is equal to 1/2, and then they added 1 to each one. 2/3 is not equal to 1/2. Okay, so all 3 of A, B, and C are doing what this front part of this is saying, that we added the same number to both the top and bottom. We added 4 to top and bottom here. We added 0. We added 1. And the original fraction would be the 2 numbers at the far left. So in this example, the original fraction was 3 over 3. They added 4 to both the top and bottom, and they got 7 over 7. And they're trying to say this is an example that shows the statement's false because 7 over 7 is not equal to 3 over 3. But that's not the answer because actually 7 over 7 is equal to 3 over 3. Both of those equal 1. So the first one's actually an example that shows that this process works, but we're not looking for one time that it works. There's no easy way to prove something's true by one example. So this is not the answer because I'm looking for a counterexample that shows it's false. I don't care about showing that it's true right now. And 1/2 was the original fraction here. I added 0 and I still got 1/2. The fraction 1/2 is equal to 1/2. See, this kind of proves that it's true again. So we got 2 examples that show that it's true. That's still not enough to say that it's always true. Because now in this third example, 1/2 is the original fraction. Add 1 to top and bottom, and you get 2/3. But this is true that 2/3 is not equal to 1/2. 2/3 is bigger than 1/2. So it worked for 2 times, but the third time I tried it, it didn't work, and that's all it takes to disprove it. You can prove a statement false. You can disprove it if you get one example that shows it doesn't work, no matter how many times it did work. Okay, so we had 3 of those in the homework. They're jumping to a new topic now. They got a pattern going on, 8, 13, 18, 23, 28, and the goal is to find the next number. Identify a pattern in the given list of numbers, then use this pattern to find the next number. More than one pattern might exist, so it is possible there's more than one correct answer. Okay. So one thing I look for is, are you adding, subtracting, multiplying, or dividing by the same amount first, constantly? Or sometimes it like goes up 1, then up 2, then up 3. Is there maybe a pattern to what it's going up by? Here it's from 8 to 13. You could add 5 to get from 8 to 13. And then if you add 5 again, you get from 13 to 18. Then add 5 again, you get 23. Then add 5 again, you get 28. So in a pattern, if you're constantly adding 5 in the part that they give you, then that implies it continues forever. So that means 28, you would need to add 5 to that, and 28 plus 5 is 33. Now you are allowed to use calculators in this class, both on homework and the tests. So if you need a calculator to work problems like this, there's nothing wrong with that. The calculator doesn't have to be very fancy. It can just be, I often just show one here I have on my computer. Here's what's called a standard, or this is what's called a standard calculator. You can have a fancier one if you have like what's called a scientific calculator or a graphing calculator. It's not anything wrong if you have one of those. But for most of the class here, at least most of the beginning of the class, you could get by with just a plain old calculator, just adds, subtracts, multiplies, and divides. Okay, 33. Okay, a little bit harder here because see how big the numbers are getting. So maybe you want to, if you think you know what's happening early on, you might want to check that with the other ones. Because now it appears 5 times 5. That's how we normally get 25. So maybe they're always multiplying by 5. Well, let's see. Does the next answer 25, if I multiply that by 5, do I get 125? Yes. And then if I multiply by 5 again, it's supposed to be 625 next in the list, and yes. And in fact, on a calculator like this, if you just, I don't even have to hit times 5. If I just hit equals again, it'll repeat what you just told it to do. Here's another times 5 by just pressing equals, and notice it's 3125. So if I press equals again, the next one should be this, 15,625. Not every calculator does that, but this one does. 15,625. Okay, so now if you ignore the front number, see how it starts off the same as the previous one. There's a 5, 25, 125, 625. That was all multiplied by 5. That has the same numbers as this one did. The first 4 of this one. But it works even backing up to 1, because if I go back to 1, literally 1 times 5 is 5. And then if I do times 5, I get 25. Times 5 is 125. Times 5 is 625. So times 5 is 3125, which was the last number of the previous problem. So that problem was kind of similar to the previous one. So once again, you can go back to a problem that you've already done. Whoops, I didn't mean to do that. Go back to number 6. And you might be thinking, okay, I did number 5, and then this one was just too similar to number 5. So if down here in the bottom right, if you hit similar question, it gives you a totally different one. And that way you could say, I didn't really learn much with that problem because it was too similar to the previous one. But now 1 times 3 is 3. Times 3 is 9. Times 3 is 27. Times 3 is 81. So times 3, the next time will be 243. So even if you get problems right, you can do them again. Any problem in any homework can be worked on as many times as you want until the deadline. So I have until Saturday night to keep working on this. Now, many students, as soon as they finish a problem or finish an assignment, they never come back to it again. But that's the best way to get ready for a test. In this class, all you do is do homework, take tests, and take the final. So if you want some way to review for tests, the best way is go back and do the homeworks again. Just quiz yourself by doing another example of, they have like 10 versions of every problem, so that way it's a different experience each time you do it. Okay, in a pattern with fractions, you want to try to do the top separate from the bottom. And one thing that can help here is that all the tops are 1s. That's not changing. So no matter what the answer is, it has to have a 1 in the top. I don't have to worry about that. But sometimes the top and bottom both change, and then you got to like kind of do separate things for each one. Sometimes the top you're adding something over and over again, and maybe the bottom you're subtracting over and over again, or dividing or multiplying. So now just ignore the top and work with the bottom. 6, 9, 12, 15, 18. 6 plus 3 is how you get 9. Plus 3, you get 12. Plus 3, you're constantly adding 3. So one more plus 3 will be the bottom, 21. Okay, so now if I thought, okay, there's nothing times 5 that equals 9, so it's definitely not multiplication. 5 plus 4 would be 9, but 9 plus 4 is not 14. So let me come back over here. Here. So I got this big whiteboard that I can write on, which is nice. So we've got 5, 9, 14, 20, 27, and 35. And then the goal is to get this next one right there. So 5 plus 4 is how you get 9. But 9 plus 5 is how you get 14. 14 plus 6 is how you get 20. 20 plus 7, see how you're adding, but you keep adding by one more. So the next one should be adding 8. 27 plus 8 is 35. And then 35 plus 9 should be the next one, which is 44. So it's okay if there's a pattern even in the pattern itself. So 44 is the next one. They love to put these kind of questions on like IQ tests, or there was that one test, Donald Trump took one of these and he was like so proud of himself that he got these kind of questions right, but they said that's usually something they give to like junior high kids. But identify a pattern. Okay, so first there's a circle, then there's a triangle, then a square, and now I get a circle again, and then a triangle again, then a square again. See, there's a pattern going on here. So every 3 it repeats. So that means I should get this circle again. And the answer would never be B. There isn't a single one that has a hole in the middle. So that's just a made up example. It could have been C or D, but that's the one I was on next, was a circle. Okay, so then these are kind of fun to play with sometimes. These pattern things that are going on. It turns out that 3 plus 6, right up here, is equal to 6 times 3 divided by 2. Because 6 times 3 is 18, 18 divided by 2 is 9, and 3 plus 6 is 9. So then what happens is, you can see there's a pattern over here on the left, and then there's a different pattern on the right. So the goal is to figure out that pattern on the right. So they went from 3 plus 6 on the left to 3 plus 6 plus 9. See, that 3 plus 6 is up 3, and then 6 to 9 is another up 3. And then you have all 3, 6, and 9 again, but now you add another 3 more higher than the last number. Then you add 3 more higher than the last number, and then in the question you're adding 3 more higher than the last number. So the left pattern is definitely easier to identify. So what's happening in the right pattern, you can look at these part by part. Don't try to do it all at once. See the 6 here? Then you go to 9. That's the last number here. 12 is the last number there. 15 is the last number there. So apparently in my answer, if I click this fractional tool button, since the 18's last here, this should start with an 18 before I get to the plus. That's one way to see it. But also another thing is 6 plus 3 is 9. 9 plus 3 is 12. 12 plus 3 is 15, and 15 plus 3 is 18. So different ways to see the pattern. So maybe it's not so obvious. Where did this 4 come from? There's no 4 anywhere else in there. But as long as the pattern is established, you don't really need to worry about it too much. 3, 4, 5, 6. That's going up by 1s. 3, 4, 5, 6. Oh, I'm sorry, I messed up here. This is times, not plus. Times is right there. But it's a pattern, 3, 4, 5, 6, so then 7. And all the denominators are 2s. 2, 2, 2. The denominator never changes. 2, So then I don't have to worry about that half. So I just look at them one part at a time. You don't have to do it all at once and try to figure out, where did this 4 come? Where did this 5 come from? Is the conjecture correct? Okay. So the idea is you'd have to check them all, but 9 times 4 is 36. 36 divided by 2 is 18. And 9 plus 9 is 18. Here's 9 plus 9, 18 plus 12 is 30. The left side's 30, so does this make 30? 12 times 5 is 60. 60 divided by 2 is 30, yeah. And 3 plus 6 is 9, plus 9 is 18, plus 12 is 30, plus 15 is 45. And 15 times 6 is 90. 90 divided by 2 is 45. So it seems to work every time. So yes, because both the left and the right side are equal to, I guess they're talking about the one that we eventually did. So 45 plus 18, if I did mine, 3 plus 6 plus 9 plus 12 plus 15, there's 45 plus 18. The left side is 63 in my example, my answer example. And so 63, does 18 times 7 divided by 2 equal 63? Yes. See, they both equaled 63 in this one. I checked that it worked for all these, and then I did my answer, and both of my answers were 63. I think that's what they want here. Sometimes it's a little hard to know what they want in some answer boxes, and you might have to get them wrong to see what they want, but okay, so now they just want to know what the next one is. So first there's a 2, then 2 plus 4, then 2 plus 4 plus 6. So the left side seems to be 2 plus 4 plus 6 plus 2 more away, which would be 8. Now, see, the right side's got a pattern. It's 1, 2, 3 vertically. 1, 2, 3, so mine should be a 4. And then the final column is 2, 3, 4, so mine should be a 5. And 4 times 5 is 20. 2 plus 4 is 6, plus 6 is 12, plus 8 is 20. See, it works. 20 equals 20 in my final one. Although they didn't have me check it, but that's fine. Okay, so notice here there's always a 137 in the middle. And they did that part for me because that was so easy. Actually, the right side here is easy to recognize. 10, 20, 30, 40. So I should have 50,000. And then it's 10,001, 20,002, 30,003, 40,004. So mine should be 50,005, my answer. It's not so obvious what's happening with 73, 146, 219, 292. That's hard to tell what's going on there. So one thing to try is, if it's getting bigger, if you try subtraction, will tell you if there's constantly something that you're adding. So if you take the second answer, 146, and minus the first one, 73, whatever that subtraction is, 73, then if I did the third one minus the second one, or the fourth one minus the third one, I should get 73 every time. So does 219 minus 146, does this equal 73? Yes, it does. Does 292 minus 219 equal 73? So what that's called a common difference. Every time I take one, if I subtract the previous one, if you get the same answer every time, that's the amount you're actually adding if you were going forward. If I was going forward, it would be 73 plus 73. That's how you get the 146. Plus 73, that's how you get 219. Plus 73, that's how you get 292. So the next one should be another plus 73, which would be 365. Okay, so here's another one where there's part of the pattern done for you. The 9's in the middle. They got that already. There's a plus 4, plus 3, plus 2, plus 1, and they put plus 0. They did the two obvious ones. So look at the far left and the far right. Those are the two you're trying to fill in. First, there's a 7. Then there's a 7, 6. 765, 7654. Not only do they keep adding a number, but the last number keeps getting smaller by 1. So 7654, and then you're going to need a 3 after that. On the right side, it started off 67, then 687, and 8 suddenly appeared in the middle. 6887, 68887. The 6 is always first, the 7 is always last. And then first there was no 8s, then 1, then 2, then 3. So mine should be a 6 with 4 8s before I get the 7. And maybe if you check the math on this, I'm assuming these are true every time. Oh, okay, maybe we can't assume that. So let's just try it. What's 76543 right here? 76543 times 9 plus 0 is itself, so I don't need to add 0. But yeah, see, it worked. 688887, 688887. So that is a pattern that just keeps producing. It's kind of weird how it produces a pattern in the numbers, but then it's also true mathematically that these two things are equal to each other. Okay, this is one known long ago. This is called Pascal's triangle. There was a French mathematician, Blaise Pascal. He lived from 1623 to 1662. And this was known well before him. Actually, about 1,000 years ago, they found it in a Japanese document from about 1,000 years ago. There was somebody working this triangle out. But it was a handwritten document. Pascal, he lived when the printing press was invented. So Europeans were like mass printing everything at the time. And it became known as his triangle only because the masses got to see it for the first time. Where in the past it was like really hard to spread it around when it was all handwritten down. So really it shouldn't be attributed to him because it was known well before him, but that happened a lot in history where white males of European descent were the ones that got credit for a lot of stuff, even though a lot of stuff was known in other parts of the world well before that. But anyway, in Pascal's triangle, this is almost like a piece of art almost. Somebody was bored one day and they just had ones diagonally to the left and ones diagonally to the right, forming a triangle. And then on the inside, what you do is, see where these two ones are right here. You add 1 plus 1 and go diagonally in between that on the next row, and that's the sum too. If I grab this 1 and 2, 1 plus 2 is 3, so halfway in between them, down below one row, you put a 3. And the graph, the chart is symmetrical too. So 2 plus 1 is 3. So when you want to do a new row, it starts with a 1, and then you add the 2 here. 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and it always starts and ends with a 1. So they just want me to do the next row. So it's going to start with a 1 and end with a 1 no matter what. And if you want to fill this box in right here, you just look up diagonally both ways. 1 plus 4, that's 5. For this box, you do 4 plus 6, which is 10. And then it's symmetrical. 6 plus 4 is 10. 4 plus 1 is 5. So notice if you go across, 1, 5, 10, and the other side's 10, 5, 1 backwards. And it's got the symmetry to it. That's all they're having you do here. But there's a whole bunch of hidden math inside of this. Not only is it 1, 2, 3, 4, 5 right there diagonally, but this is another pattern we saw. Here it's going up 2. From 1 to 3, it goes up 2. From 3 to 6, it then goes up 3. From 6 to 10, it goes up 4. There's one of those ones where it's going up, but it increases by 1 every single time. And then there's even some other math hidden in here, and if I have some extra time, I can show you that at some point, but let's make sure we cover what's in here first. Okay, so this one looks a little complicated. We have 6 minus 2 squared equals 36 minus 24 plus 4. 8 minus 5 squared. Okay, so use inductive reasoning to do this for this one. Okay, so there's only 2 things in the parenthesis. And it's actually a very common misconception when people get a problem like this in math. they think they can just take this square exponent and do it to both parts. And it is true that 6 squared is 36. 2 squared is 4. Those are both there. But there's an extra number in the middle. So 12 squared, which is 12 times 12, is 144. My answer should definitely start with a 144. And both of the examples they gave had a minus next, and it maybe is not so obvious where that middle number comes from. And I'll just leave some space there. Okay, and then there's a plus in the back because actually anything squared is positive. So if you do 6 squared, you get positive 36. And even if you do negative 2 squared, that's still positive 4. 8 squared is 64. Negative 5 squared is positive 25. So 12 squared is 144. Negative 8 squared is positive 64. So I got 2 of the 3 answers at least. The only hard part is how do you get this middle one? And you might not know this without having somebody show you this, but there is a reason where that number is coming from. It turns out to get that middle number, what you do is you multiply these two together. 6 times 2 is 12. And then you just automatically double it. Take that answer and multiply by 2. And whatever this sign is, that's what it's going to be. So you could do this with a plus too. They don't have any here with a plus, but you could do this with a plus. And it would get you the same answer. You'd get your 36 first. You'd get your 4 at the end. And then you'd get this 24 here, but it would actually be plus. If there was a plus here, this would be plus. But with a minus here, this will be minus. So that's where the minus 24 is coming from. So it's going to be minus for sure. And I already put the minus here too. And then you just do 8 times 5, 40, and double it. 8 times 5 is 40. Doubled is 80. So if I do 12 times 8, and then double it times 2. It's always times 2. That's got to be a 192 right there. And that would be hard to do without a calculator. So, okay, so I've answered all 15 questions in section 1.1. And you can't see it, but if I aim right here it says I have 100%. 15 out of 15, I got a green check here. So at any point, you don't have to do a whole homework in one sitting, but if you stop at any point and just hit save, you can pick up where you left off and continue at another time if you want, as long as you get it done by the deadline. So it's due July 22nd, 11:59 p.m. That's Saturday night. And I did it all in one sitting, obviously, but I could have done a little bit on Monday and come back on Wednesday and did a little more on Friday. But really, you should try to keep up with the calendar and do in each video, you should at least try to get that far. Try to do all of 1.1 and 1.2 on Monday. If you put it off and get behind, it's very hard to catch up. And then right before you take a test, you got Friday and Saturday, 2 days to study and take the test. And most people are going to wait till Saturday. If you want to do it on Friday and get it over with and not having to do anything on the weekend, that's fine. That's why I give a 2-day window for it. But some people are like working all day, all week, and they'd rather do the test on the weekend when they're free. So it just gives you the flexibility to do it either way. And then so most students will not take the test till Saturday, and some will wait till really close to Saturday night to do it. Don't wait too close to midnight on Saturday, because what if your internet goes out or you get some kind of tech issue and you miss the deadline? There's no way to make it up then. But it's fine to wait till Saturday to take the test. And the best thing is get all the homework out of the way Monday through Thursday, and that way you got both Friday and or Saturday to go in and try some more again. Go in and say, oh yeah, this problem was easy. I don't need to do that one again. Oh, wait a minute, this one, remember I had a lot of trouble with this one, or right now I don't even remember how to do it. That's your cue to do the problem again. Go in and say, okay, this number 11 was hard, even though I already did it again. Even though I already did it, I can just hit similar question. And it gives me a totally different one. It's a different experience every time you do it. Now you might be saying, what if I get it wrong the second time and I already had it right the first time? I'm intentionally putting a wrong answer here. It'll tell you, anytime you get one wrong, it tells you it's wrong and tries to tell you what you should have been doing. And then it gives you another chance to do it, and then I'm still wrong, and then it says final check. So when you get it wrong now it puts a red X for this problem, but it doesn't mean it's wrong forever. So, and if that was the first time I did it, it would just mark it wrong. But since I previously got it right and now I got it wrong the second time, you can either save this attempt and punish yourself and lose your points and try again, force yourself to do it again, or notice the default is save best score. So if you save best score, you don't lose your points. I still have 100% on this assignment. And I did get this attempt wrong. And now if you click the answer box, it'll tell you what the right answer. No, it shows the right answer here. If you click it, it shows what I answered. So maybe I could see from what I did wrong, oh yeah, look, I didn't even finish that side, and this was supposed to be times and I'm doing divided by. Some students find this like a teachable moment where they, by getting it wrong, they can tell what they did wrong. And this is the purpose of homework. The homework isn't meant to bog you down for hours and hours and hours to just make you jump through a hoop to get a grade. It's to get you ready for tests. So use it as needed, and if you think it's easy and don't need to do it ever again, that's fine. But a good way to study for the test is just go back in and you don't have to do every problem a second time, but just scroll through and say, okay, that one was okay, and I think I understand this one, and then, no, let me try this one again. That's your best way to review for tests on Friday and Saturday. Okay, so now I'm going to click assignments again. They said they were doing some maintenance on this, but it wasn't supposed to happen until tonight. Let me try to come out of here and go back in. Okay, hopefully that was just a glitch. Okay, here we go. Okay, so here's section 1, 2, and it's got 12 problems. Sometimes they do maintenance on this thing, and in worst case scenario, sometimes we used to give tests in the testing center, and it'd be like the day that people had to take their test, they would do maintenance and it would be down all day and they couldn't finish their tests. But luckily, usually it's not that big of an issue. Okay, so section 1.2, we are doing rounding. Rounding is a big part of math, and you might be surprised that even people in calculus have trouble with rounding. So here's a big number, 78,373,785. Let me write it down over here again. Okay, so it was 78,373,785. Okay, so the first one wants me to round to the nearest hundred, not hundredth, but 100. So this is the ones, tens, and hundreds. This is the hundreds place right there. And then it goes thousands and 10,000s and 100,000 and million and 10 million. So I first have to decide, where do they want me to go to? They want me to do the hundreds. So that means everything before that you're just going to rewrite. 78,373. And then one of two things is going to happen. You're either going to keep this 7 right here, or you add 1 to it. It's always stay the same or add 1. If the next digit is 5 or higher, then you add 1. And the 8 is 5 or higher, so I have to add 1 and turn it into an 8. And if we're doing regular numbers without decimals, then you can't leave blanks at the end. Otherwise, you're changing the size of the number. So anything after that just becomes a 0 at the end. So this is the way to round to the hundredth. 78,373,800. I don't care about the 85. I'm just rounding to the nearest hundred. 78,373,000 and then 800. If that 8 had been 4 or less, I would have just left it 700. Okay, next, same number. They just want you to round to the 1,000 this time. 1,000 is this next spot right there. So, again, just look at the next digit behind it, although you should look in the original problem. There was a 7 there, so that means I need to add 1 to this 3. So part B, you're going to write everything in front of that the same, 78 and 37. And then either this 3 stays the same or you add 1. I have to add 1 because there's a 7 there. So it'll be a 4, and then everything after that's just a 0. And this is 4,000. That's why you're rounding to the 1,000. If you just read this much of the number, it would be 4,000. So everything else is there, though. 78,374,000. Actually, I should have put a comma there. 4,000. And they're just moving up 1 digit every time. So now they want the 10,000 place. The 10,000 is this 7 right here. And the next digit behind that one is a 3, which is not high enough to add 1. So now you write everything in front normally. You write these 3 normally. 78,000,003. And now this 7 is not going to change. It's going to stay a 7 because the next digit's not 5 or higher. And then I need to put 0, 0, 0, so there's no empty spaces. 78,370,000. Okay, 100,000 is the next place in line. This is where the 3 is. This time there is a 5 or higher after it, so I need to add 1 to this 3 and make it a 4. So 78,400,000. 78,400,000. And we got 2 more. Now they want the nearest million. Million is where this 8 is. And there's a 3 behind it, so I don't need to add 1. Just keep it 78. 78, and then everything after it's a 0. Literally 78 million. Imagine if you had $78 million. Finally, they want all the way to the 10 million, which is that front 7. Since there's a 5 or higher after that, you would add 1 to the 7 and turn it into an 8. And then everything after it would be zeros. 80 million is rounded to the nearest 10 million. What's a couple million between friends? Okay, so that's how you do big numbers. Usually rounding involves decimal numbers. It's much more common to do decimals than large numbers in the millions. So I've got this long decimal right here. And this is just one part instead of doing it 6 times, but they just want me to round to the 1,000th. Notice the TH at the end there, 1,000th. So one weird thing is that on the big number side, if you take a regular number that doesn't have a decimal, there's technically a decimal at the end. And then you can put as many zeros as you want after that. Zeros at the end of a decimal don't change it. So the first number to the left of the decimal is called the ones place. This is the tens, then the hundreds, and then you get 1,000, 10,000, 100,000, and so on. The strange thing is that the first decimal place to the right of the decimal is called the tenths, with a TH, tenths. There is no ones. So it goes tenths, hundredths, and then thousandths, and so on. So this one wants the hundredth. I think it said hundredth. So that's the second decimal spot. No, I'm sorry, it said thousandths. I misremembered it. That's the third one. So I have 1.540, 1.54062, and they say thousandths. So when you start counting, you start with the tenths. This is tenths, hundredths, thousandths. So I want to stop right there. So wherever you realize you're stopping at, you either write it down just like it looks. You're either going to write that 1.540. That could be the answer. Or it's either that or you add 1 to the last digit. So it could be a 1 instead of a 0. It's one or the other. That's all that ever happens. And it all depends what's after it. The next digit only. If that next digit is 5 or higher, then you add 1. Otherwise, you don't. And it doesn't matter what else is happening. If there's more decimals, the rest don't affect it. And even though you can add zeros like we did here, Zeros here matter because it changes the size of the number if you don't put them. But you can add zeros to the end of a decimal, it doesn't change it. So we normally don't put extra decimals at the end of these when we decide where we want to stop rounding at. So I'm not going to put these extra zeros here, but I'm going to just put 1.541. I do need the 1 and not the 0 because there's a 5 or higher right there. 1.541. Okay, so nearest 100,000th. 100,000th. We start a new one here. 2.031. First, write the whole number down. 2.031, 65166. They want 100,000th. 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 Okay, so it goes tenths, hundredths, thousandths, 10,000th, and then 100,000th. There it is right there. So my answer is either up to that point, just like it looks, 2.03165. That might be the answer. Or I might have to add 1 to this 5 and make it a 6. That's all that would ever happen. And if so, the rest would be the same, 2.03166. So it's either 165 or 166. And it all depends what digit's next. If the next digit's 5 or higher, you go to the 6, otherwise you leave it a 5. The next digit's a 1, so I'm going to leave it as a 5. And you don't need to put any extra zeros at the end, so that just gets ignored when decimals are going on. So 2.03165 is the answer. So you have to know how far down the line to go to, and then you have to look at one digit past that. And this is the same thing just in multiple choice style. Round to 9, they can just tell you how many decimal places instead of naming it too, because maybe that's like the billionth or something like that. That's hard to say. But they could say 10th, 100th, 1000th, or they could say 1, 2, 3 decimal places. So it's a little easier if they say how many decimal places. 9 decimals. Just count to the 9th one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right there. There's a 1 right there. So I'm either going to leave this a 1 and everything before it's definitely the same, or I might have to add 1 to it to make it a 2. And because there's a 6 right after it, then yes, I have to add 1 to make it a 2. So everything in front of that should be the same. There should be a 2.7108758. All that's there, and then it'll be a 1, 2. 1, 2. All the way to the 8, all the answers are the same, and they just change the end to either 13, 11, 12, or 20. But really, it would only be 11 or 12 would be the only 2 possible answers, actually. This one would be 12. If that 6 was a 4 or less, it would have been 11. Okay, then this is a very good technique or skill for you to have even in everyday life. If you go to a grocery store and you want to buy stuff, especially with inflation being bad, it's kind of good to, in your head, be able to estimate prices and figure out roughly what your price is going to be at the end in case you're spending too much money, rather than waiting until you get to the checkout line and then, oh, that's too much, and having to give stuff back kind of embarrassingly. So one strategy for this is, I'm reading here if they're saying anything. Okay, so what I would do is take $6.77 and just round that to $7. And definitely $2.01, round that to $2. And then 12.15, round that to $12. Just round to the nearest dollar. So $7 plus $2 is $9. 9 plus $21 is 9 plus 12 is 21. So, and I was looking for this in the paragraph, but here it is down here. It says round each number to the integer. I wasn't sure if that's what they were doing, but that's a common strategy, yes. So that's $21. That could possibly be done in somebody's head. Then, and you probably maybe have a calculator on your phone, so this might not be as important a skill as it was maybe back in the 80s or 90s, but if I do 6.77 plus 2.01 plus 1215 with a calculator, how close was my estimate? See how close that was? $20.93. And I said 21. So it was a quick way to see how much money I was going to need, and I wouldn't have to like, oh no, I bought too much more than, I don't have enough money to spend on this. So estimation skills, not only are they good in real life, they're good in math too, especially like on tests. If you can do that sometimes on a test. Sometimes people get answers that are just completely impossible if they would have used a little bit of estimation techniques. How reasonable? It's very reasonable because it was very close to the answer. It was a little, the estimate was a little higher. The estimate was 21 and the actual price was $20.93. But that's pretty reasonable. It was only off by 7 cents. So reasonable, and the estimate was just a little higher. Same thing here. Take this 2805 and make that 28. And why not make the 18009? That's close to 18. Why not just do 28 minus 18? You could probably do that in your head. 28 minus 18, the estimate would be 10. What's the actual answer with a calculator? Let's see how close we got. 2805 minus 18.009. The answer is 10.041, which 041 is very small. If I round to 2 decimal places, that's like $10.04. If you were off by 4 cents, that's no big deal. So that is reasonable. It's very, very close. The estimate, though, is smaller than the actual answer this time. Last time it was a little bigger. Now it's a little smaller, but it's still pretty close. So the estimate is a little lower this time. Especially when you get to multiplication. So here's a couple of things we might do here. 20.25, that's pretty close to 20. It's closer to 20 than 21. And 8.5, now when it's in the middle like that, when you're 8.5, you're going to round that to 9 actually because of the 5. 5 or higher, you round up. But sometimes estimates aren't the greatest if you are kind of in between like that. So I would do 20 times 9 for the estimate, which maybe you can do that in your head because 2 times 9 is 18. And then you just put a 0 on the end of it. But if I would have went the other way with 8, that would have been 160. See, 8.5 is in between these two. So sometimes if you really are going far away from the number, that can make a big difference in the answer. An extra $20 on a price of something, that could make a difference. So I think they want the 180 just because 8.5, the rule is you round up if it's 0.5 or higher. So let's see how close. This one might not be as close as the last two were just because of what I was talking about 8.5 being pretty far away. See, 172. Now you're not just a few pennies off. Now it's like $8 off, which that's not a huge difference, but it's not nearly as close as the last two examples were. So 172.125. It's almost like $10 off. And so now they're using a different rule here. And really, they didn't specify a rule before. Just the other two were so close. There was no doubt that those were close. Here they're saying if you're at less than $10, then that's considered close enough. So this is less than 10, but just barely. So at least it's in the ballpark. Say you were like trying to pay for a hotel and it was like $20 a night. That's not a good example of $20, but $20, you're renting a room, $20 a night for 8 or 9 nights, then you can figure out the price pretty quickly. And if you're within $10, that's reasonable. Okay, what about division? So 35.86, I would get close. The closest integer to that is 36. And that's fairly close to 36, actually. 35.86. And then 2.9 is pretty close to 3. And it turns out 36 divided by 3 comes out evenly. That's exactly 12. So there's your estimate that you could possibly do in your head. Quotient is another word for division. So clearly we would need a calculator to do the actual answer. 35.86 divided by 2.9. 12 point, how many? See, it says round to 3 decimal places. So I want to definitely go to the third one, which is this 5 right here. If the next digit's 5 or higher, you add 1, otherwise you don't. So the next digit is 5 or higher. I need to change this 5 to a 6. So 12.366. That's pretty close. It's less than half of a unit away. And then we want to see, is the estimate higher or lower? The estimate is 12. The actual is 12.3. The estimate is a little less than the actual. And it is pretty reasonable because it's fairly close, 12 versus 12.3. Here, they're not giving me a rule about how far away does it have to be till it's not reasonable, but usually when that happens, then it's so close that it's obviously close. Okay, what if I want to rent a car for $305 per month, or lease a car, I guess, and then do that for 4 years? Estimate the total cost by rounding the monthly payment to the nearest 100. Okay, so we're doing $305 per month, but round to the nearest 100. So we did that earlier. 305. If you're rounding to the nearest 100, one, tens, and hundreds right there. I'm trying to round to this number. The next digit is not 5 or higher, so I leave that as a 3. And this is without the decimals. This is where you put all zeros in the back. So $300 is the closest 100 to 305. And you're doing this for 4 years, but you pay for cars monthly. So we need to convert this to months before we multiply. There are 12 months in a year. So 12 times 4 is 48 months. And if we're estimating first, we should round this to 50 probably. That way it's very easy to do 300 times 50. When you're doing numbers that end with zeros, you can ignore the zeros till the end. Just do 3 times 5, 15, and put 1, 2, 3 zeros on the end of the answer. So if you're trying to lease a car or buy a car, you could do this. Get your monthly payment and just round to the nearest 100. How many months are you going to pay? Round that to the nearest 10. And then that gives you a quick idea. This is what you're going to pay for the car. $15,000. Either if you're going to pay it all up front, or it'll be monthly payments it'll be broken into. So the estimate is $15,000 for the total cost. Total cost of the lease, okay. Nearest 100, okay. Maybe they didn't want me to round the month to 50. What if I did 48? Let's try that. 14,400. See, sometimes you have to get these wrong to see what they want actually, but 14,000. What did I say? 14,400. Okay, so I wasn't sure. So I did something I wasn't sure, and then it turned out that was wrong. So I would go ahead and do this because I was able to do this in my head. I couldn't do the 300 times 48 without a calculator. So, I mean, I could, but it would take a little longer. So that's why I thought maybe they wanted that rounded to 50. But again, that sometimes you just have to get it wrong to see that, no, they didn't want me to do that. Okay, so the actual cost is that you should do 305 times 48. Because you actually are going to pay $305 every month. So it makes the total cost a little higher to $1,460. Or another way of thinking about it is your estimate is lower than what you're actually going to pay. If they ask for that. Okay, the estimate is a little higher. The estimate is a little lower. Look from the estimate's point of view. 14,400 is a little lower than 14,600. The estimate is a little lower. And the difference is, whenever you're doing a difference, just subtract the bigger number first. So do 14,000, trying to see it so you can see it. 14,640 is the bigger number. Subtract the 14,400. That's the difference. There's a difference of $240. So you check this B option where the estimate's a little lower, and it's lower by $240. So you will pay more than you thought, but at least you were close. When you're talking $15,000, $200 isn't that big a deal. Okay, so even a problem like this, estimation helps a lot. Even if you have a calculator, it's kind of good to do this ahead of time just because it's very easy to have a typo in a calculator. And somebody just types it in their calculator and thinks they got it right, and it's wrong. It happens to me a lot, too, in my other math classes. So with estimation techniques ahead of time, if you know roughly what the answer should be close to, and then your calculator gives you a totally different answer far away, then you know you must have had a typo. And I can't tell you how many times I'm grading tests where a student has the right work and they just have the completely wrong answer. And I can tell they must have just typed that wrong in their calculator. And if they maybe had used estimation techniques, which what this section's about, they could have known that answer can't possibly be the answer. It's too far away. So again, I don't know exactly where they want me to go to, but this is what I'll show you what I would do first, and then I have to see if this is what they want or not. I would take this big messy thing right here and just get it to one decimal place. 2999, that's very close to 0.3. If the next digit is 5 or higher, you add 1 to this one, add 1 to that 2, and make it a 3. And 106 is very close to 100. Why don't we just use 100, which is nice to work with? And just make this 0.6 because the next digit's a 0. I don't need to add 1. I don't know if this is what they want to do, but this is what I would do. So 0.3 times 100, whenever you do a decimal times a number that ends with zeros, the number of zeros you have is how many places over this goes. So 0.3 times 100 is 30. Because you move the decimal once to get past the 3, and then once more, and then the decimal's technically in the back when you do that. So that's 30. 30 divided by 0.6 is still not easy to do, but if you want to get this 0.6 to be a regular 6, which would be preferred, you can do that if you add one more place up here and make this 30 a 300. And now it's easier to do because 30 divided by 6 is 5, and then you can tack on a 0 and the answer is 50. So I have a very rough estimate of this answer that it's close to 50. So if I type in my calculator and I'm not anywhere close to 50, if I get something like 4.8 or 497, I'll know that must be some kind of typo because the answer should be reasonably close to 50. And see, that's one of the choices. 50 is one of the choices. So which of the following is a good estimate? 50 is. So I wasn't sure the way I did it if it was exactly the way they wanted to do it, because on the last problem I rounded that 48 to 50 and it turned out they didn't want me to do that. So now let's take out a calculator and just do it in there. If I do 0.29926 times 106 divided by 0.604. So 52.5. So it's close, but not necessarily extremely close. They want me to round to 2 decimal places. It says right here. So I look at the second decimal. There's a 1 right there. I'm either going to keep this 1 or add 1 to it to make it a 2. Since the next digit's 5 or higher, I need to add 1 to it to make it a 2. So it's going to be 52.52. And again, look at the estimate. The estimate's 50. The actual answer is 52. So the estimate's a little bit lower. The estimate is a little lower. How much lower is it? Just do the bigger number minus the smaller number, even if the estimate's higher. 52.52 minus 50. It's off by $2.52. If this was money, maybe it's not about money, but... Okay, we got 2 problems left for today. Okay, here's reading graphs. That's a skill that helps to know. When aging, body fat increases and muscle mass declines. The line graphs show the percentage of body fat in adult females and males as they age from 25 years old to 75 years old. Part A, find an estimate for body percent fat in 35-year-old males. Okay, so the chart shows the red are females and the blue are males. So they asked for males. I only care about the blue graph right now. 35 years old is on the chart right there. So I find 35 age. I go to the blue graph because that's males. Now the dot's not exactly on a mark. This mark right there would have been 24. And then if I went up 2 more spots, that would have been 28. Halfway between 24 and 28 is 26. So they didn't mark it, but this line here would be 26. So I'm somewhere between 24 and 26. Why not just cut it in half and say 25? So that's at least an estimate. It may not be exactly 25, but I would estimate that to be 25. It seems to be halfway between 24 and 26, or at least close to halfway. At what age does the percent body fat in males reach a maximum? So the maximum is the highest point of the graph right up here. And that's 28% for the fat, but it's 65 for the age. They might ask for either one. Here they're asking for the age. What age does it happen at? So the highest point is right there, and the age that occurs is 65. So apparently males get fatter and fatter until they're 65 years old, then it starts declining. What is the percent body fat for that age? See, that's the other half of the graph. So if you're at this spot exactly, and notice they made it land exactly at a spot so that it's exactly at 65 years old and it's exactly 28% body fat. So they asked about both of those at that one spot. Okay, what age do males have 24% body fat? So find the 24 here, and then go across till you hit a dot right there. Age 25 is the answer. Okay, I guess this is just a little extra piece of knowledge to know. So on the test, when you take your tests, every problem on the test is a homework problem. It's like try another version of it. Now, some of these kind of like just informational ones, you're probably not going to see this on a test. Or if you get a crazy hard one, maybe there's one that like that I get it wrong, or I take a long time to do it, you probably won't see that on a test either. But any of the rest, just they're good practice to do over and over again. So this is just for informational purposes only, but the point of estimating is when I say that 0.29926 is close to 0.3, or that 106 is close to 100, the way they do that mathematically is you write the original number, and then instead of saying equals, we put a squiggly equals. That's a way to tell somebody else that you're doing this. If somebody else saw this, they'd say, okay, this long decimal is approximately equal to this shorter one. That symbol means approximately equal. The symbol squiggly means approximately equal to. Just so you know that. Okay, so I now have, I'll tilt it again right there. I now have 100 on this one too. I can save this. So as long as you don't punish yourself and take less points by redoing a problem, once you get hundreds or once you get a high grade on them, then that's never going to change. So if I click assignments over here on the left, click assignments, although it's acting up again, I got to go to course and then assignments. Each time you finish one or each time you stop doing one, for some reason they do this over here on the side. See how it says C score? So I can click that and say, okay, I got 100 on that one. C score, that one's 100. But if I do this third one we haven't done yet, I have a 0 on that one. So that way okay, I'm finished with these two. And then I finished these two on Monday. Monday, July 6th. What day is today? July 17th. Monday, July 17th. It's good if you can do both of these that day. And if you don't get 100 on both of them the first time, that's fine too. But you don't want to put it off and try to do it all Saturday an hour before you're going to take your test. You just won't finish it all. Plus, if you really want to get a good grade on the test, it's good to do all the homework during the week when they're scheduled. They're not due till Saturday night, so somebody could do them all Saturday night. But if you do them all through the week and follow my videos each day, then you can spend the Friday and or Saturday practicing more, and the more you practice, the higher your grades are going to be. Because if you just do it one time, it's easy to forget it when you get to the test. Okay, during these videos, I also plan to give you a little magic word of the day, and I forgot to do it. I'm going to try to hide it somewhere in the middle of the video because I don't want somebody just watching the beginning or the end and get credit for just watching part of the video. So at some point in a video, I'm going to say a magic word, and then all you have to do is email me. Let me put this right here. Send an email to richard.a.prather at lonestar.edu. And this is in the syllabus too, but just email me. For each video that you watch, you get credit for watching them as part of your homework grade. So to prove that you watched it, what I'm going to do is just have you email me a magic word of the day. And this first one, I guess since I waited to the end to do this anyway, I'll just put it here. But from this point going forward, it'll be somewhere in the middle of the video, unless I forget again. Sometimes I forget, but I'll try to hide it somewhere in the middle of the if you're paying attention, you'll know it. And if you're not, you'll miss out on it. And then today I'll write it down, but I'm not going to write them down because I don't want somebody like going through and fast forward just looking for the magic word that's written down. So today's magic word, since our college is in the Houston area, I'm going to do NASA today. Send me an email. In the subject, you can just put magic word of the day. Magic word. And put today's date, July 17. Even if you're watching this video on a different day, that's okay. But the magic word of the day for July 17th, for people that were watching this first video on the day it was scheduled to be watched, is NASA. Send that to me and you get credit for that. So each week you'll get a homework grade. I'll average all your homework together at the end of the week. You get a homework grade. And then I'm going to give you 1 point for each magic word you send me that's correct, and average that for the week too. So when you take your first test on Friday night or Saturday night, or Friday or Saturday sometime, you'll see your grade update, and it'll have a homework average for the week, a video average for the week, and then the test score. And then we do that for 4 weeks. And then in the 5th week, we review. So the homework grades will be reviews for the final. There are reviews for the final. And then I'll do a magic word for each of those videos too. So this is it for the first video of the semester. We'll do videos every Monday through Thursday. There's 4 videos per week because I cover 2 sections per video, and there's always 8 sections to do in a week. So this is the end of the first video, and send me that magic word of the day to get credit for watching this video.